Okay, all right, sit down. So, today we want to discuss some issues in organic chemistry basically. So, as far as my own experience is concerned, if I talk about the experience that I personally have had for this long time, that after doing organic chemistry of for an around decade this way or the other, I have somewhere in conclusion that organic chemistry seems to be very puzzling at surface level. It's very confusing kind of, it's a messy stuff. For most of the school, college students, if you speak to them, they will often claim it's very elusive, confusing and messy structure of organic chemistry. And I share this feeling with them, the fact is this. But once I developed an approach to our organic chemistry and met some good books, and the books like the one Claydon Chemistry, and there are other books, just when before Claydon Chemistry there was books called Morris and Boyd, which was close in approach to the Claydon one. When these kind of stuff that I have been through, I have some different perception, I reached some different feeling, got some different feeling about organic chemistry. And from being organic chemistry, from being little confusive, as people call it, elusive, not clear, to very clear, systematic, organized kind of thing. From this state of chemistry at 10+2 level or school level or to some extent college level, you came to this level at doing when you are doing chemistry at little advanced level. And the difference, yes, of course, I have found people, those who even call that organic chemistry you can do in two ways. It looks like you can do in a way of that art is being done, means you may lead to a BA degree, that is obviously possible, but it can also do it by completely scientific approach. I am for the opinion that whether you do it by this way or that, by an artistic manner or purely scientific manner, since what is art and what is science, whether science is art or art is science, is still not clear to the men who are deliberating on such high issues. So I think that is not the problem. The problem is the approach. Why organic chemistry or organic people or students who have just started doing organic chemistry, why they have a different kind of feeling? The basic reason behind this is the approach. If you approach organic chemistry as a subject just to cram it, it will be difficult. But if you try to understand the basic principles, prerequisites, I will call it prerequisites for organic chemistry, it will be a way easier business, way easier and fascinating, I would say, fascinating. Organic chemistry is something which is very fascinating once you discovered its original character, that how an organic chemistry at elementary level, school or college level, part of the learning is concerned, how this is approached, how this should be approached rather. If you reach and find this idea, it will be much easier than what you have a feeling in most of the cases most students have at the starting level. So what are this way and prerequisite? What is that way that I am talking about? Way or prerequisites? What are these things? This is nothing but certain aspects, certain elements of, I think, by which or with the help of which the whole subject is made up of. What happens generally in our usual experience, we often ignore certain aspects of this. We often ignore certain aspects of organic chemistry. Let us do it by an example. If there is a carbonyl groups, and if there is some nucleophile, here is a reaction, and here is a product of this kind. Here is a product of this kind of, or something. This is the reaction, typical reaction at a carbonyl center. Typical reaction, what happens? There is a carbonyl functional group and there is a nucleophile is interact. This is the intermediate which is being treated properly. You will end up with a project. How many factors will be influencing the path, the outcome, the rate, or the manner of these reactions? Or you have to, means organic chemistry, to one point I would like to tell you, not just even organic chemistry, anything which is systematized, organized body of experimental knowledge and is originally a science, by learning that if you could not predict something in that, of course there is some bigger issues with you. There are bigger issues with the part of the learning. So you must be productive enough. You must be productive. And this power of predictions become more important in the area of organic chemistry. Means how? Unlike economics, if you are doing organic chemistry, you must be able just by seeing the reagents of reaction, you must be able to predict the product. Means this requires power of prediction. And if you attain this power of prediction, you should console yourself best that you have learned the discipline that you began to learn some years back. So this is I guess this is the test kind of thing when you can assure yourself that yes, I have reached some level of doing organic chemistry or something. Then how this power of prediction in organic chemistry or in terms of organic reaction could be achieved? If anybody comes from anywhere, any fellow falls down before you from anywhere, and he says this is the X and Y, give me the product. Tell me the product. If anybody asks questions like you must be aware. You must be able enough to at least comment on the product at least by certain degree, at 90% degree of certitude. Then you must consider yourself that. Or let's say he tells you the reagent A and B, he tells X and Y is the reagent, he asks for your product. You must be able enough that you should ask to that fellow that what are the reaction conditions you are giving to me, because reaction conditions can alter the outcome, have a potential to alter the outcome in organic reaction completely. You must be able to ask such kind of questions to that fellow, otherwise you are having a wrong approach. People generally have approach, if you ask that what is the product of X and Y in this case, people generally, a typical reply, this beginner's reply in organic chemistry, you also know I never, actually yes I have learned somewhere but I forget. This is, if you are asking or replying to some organic reaction this way, this is my own way of conclusion that you are in faulty ways. You have not learned things properly. You must be able at least to have a qualified guess that what could be the product. And this power of guessing, qualified guessing or prediction can be attained in simplest step. If you have a proper, right approach to the subject, you will automatically predict. Suppose if I said that this is the reactant and this is the product, and I mention the temperature of the reaction at 25 degrees centigrade, and if you have a good understanding of the thermodynamics of the reaction, you will soon question me, no, mister, you have addressed the question that it is at 25 degrees centigrade, but in my opinion, it must be somewhere at least 30 degrees centigrade. If you have such kind of guess making ability, a prediction ability, you understand the business of organic reaction. Or I say it takes just a 1 hour time and this is the 80% of the 90% of the product got formed. If you have a proper understanding of kinetics of the reaction, if you could guess or predict the kinetics of this part of the reaction, you will soon questioning me, no, I guess I am thinking that you are telling that this reaction is taking just 1 hour's time. This is quite not possible in such frame of kind of this parameters of experimental control. This 1 hour cannot lead to the 60% or 80% completion of this reaction if you have a proper knowledge of kinetics. Alright, if I comment something on the stereochemistry of this product, geometry, this is R or S kind of thing, plus or minus kind of thing, this stereochemical outcome I am telling you. And if you are able, you are smart enough that you can understand the stereochemistry of this reagents involved, these reagents involved in the reaction, and if I am trying to predict and trying to tell you something which is wrong, you will soon question me. If you are clear enough in a stereochemical approach to the reactions, you will soon question me, no, you are telling that the product should be S, but I guess this should not be S, the major or dominating product will be R, or the absolute product will be having R or S, or this reaction is complete asymmetric induction reaction or racemic mixture or any kind of things, if you have a proper understanding of stereochemical aspect of the reaction. Alright, stereochemical. Or if I say whether this will react or not, or what could be the possible mechanism of this reaction. These kind of things could be addressed if you have these prerequisites, which I am going to list down here. What those prerequisites could be? Prerequisite could be knowledge of reaction thermodynamics, reaction kinetics, stereochemical aspects, molecular or electronic aspects. If you are aware with these kind of aspects of that particular reaction, if you are aware with these factors, then you will soon question me, no, that this is not going to be the outcome of this reaction, or this would be possible product of this reaction. If these kind of things you are aware with, then you will be in a state where you will find consolation for yourself at least. Alright, isn't it? And one thing I would like to mention it here, especially because if I am mentioning reaction thermodynamics, thermodynamics is an independent discipline. Basically, if you are talking about reaction thermodynamics, means it is the application of some fundamental principle of thermodynamics to the kind of things that we call reaction system. So you must be clear of two things, the principles of thermodynamics and reaction itself, and how at these two, how reaction thermodynamics at least it behaves in case of reactions. So you must be clear of these aspects of the thermodynamics. If I am talking about the kinetics, you must be aware of all the factors associated with the general kinetics in general itself, and with respect to the given reaction, that how the kinetics going to play a role in this reaction or in that reaction or any kind of that reaction in a question. Stereochemical aspect, you must have stereochemical understanding, means geometry, symmetry, alright, 3D view, orientation kind of thing. Once you understand it, then you will be able to comment on the stereochemical aspect of this reaction. Alright, and third thing is molecular structure. This part demands, when you will try to do reaction mechanism, if you are trying to comment on reaction mechanism, you cannot do away with the dispensability of something called molecular structure. You don't know what is the exact molecular structure of the system, how can you be able to comment on something that how these two species are going to react? Or on this side, electronic factors. Okay, just I will gonna treat this carbonyl system in a little elaborate manner, and all these factors will be evident to you almost. Soon will be evident to you. Okay. So organic chemistry, even at some level, one may think that organic chemistry is nothing but it is just cramming a few patterns, few known patterns. If you just put these two kind of chemicals, the outcome going to be in this fashion. If it is, I think reducing the whole discipline to some fixed patterns, it's difficult, risky, I guess, rather, because outcome may be altered in organic chemistry in some amazing and astonishing ways. So reducing the subject, I think would be a misuse of reductionism. All right. So let me consider that how this reaction actually proceeds. I am considering a typical reaction on carbonyl systems. Let's say if it is a reaction, it's a carbonyl system. It's a carbonyl and it is a nucleophile, negatively charged. What is nucleophile? You must be aware of. There's something looking for nucleus, or it is attracted by the positive charge densities. So anywhere, if these two are the reagents, these are the reagents. What happens? These two are the reagents. Means this is a nucleophile. Nucleophile is name which refers this kind of molecular species or entity is looking for or searching for something positive. Then you have to search that this is then reagent, this is the substrate. Then in substrate, what are the parts that are positive? What are the possible positive centers in this part of substrate? And this requires what? This calls for what? This simply calls for a knowledge of the molecular structure of this carbonyl system, isn't it? Then how this carbonyl system is made up of? If I try to make it more clear, this is carbon, this is sp2 carbon, this is carbon associated oxygen bond, this oxygen has two pair of electron, and this is also a carbon center, this is sp3 hybridized also associated with 3 hydrogen. This is the clear picture of this carbonyl center. It is a sp2 center, 180 degree planar, isn't it? This is the sp3 center, tetrahedral, TD. This part is a tetrahedral system. This is the sp2 center. And this nucleophile will attract to which part of this carbonyl system requires its general structure, molecular structure, which at least you will understand if you understand properly what is the covalent bonding. If you understand the covalent bonding, and of course because almost all the bonds in the system involve are covalent bonds. So you must be aware of hybridization kind of thing, molecular orbital theories, covalent bonding. These kind of structure means knowledge of molecular bonding is required or not? It's obviously required, indispensable. And once you know that this is the system, this is the sp3 hybridized system, this is the sp2 hybridized, this is this, the overall structure of this molecule is what we call planar. This is a planar system. C2 axis passes from here. Since these two, this part, this side and this side of the system is called similar. A dash side is similar. That's why it's a symmetric. That simply means it's a symmetric phase. This is what? Stereochemical information, geometrical information to this reaction site. Although in this case, this is the simplest possible case, to this geometrical and stereochemical constant are little less relevant. But if I introduce an carbonyl, I think if I introduce some kind of sp3 center, asymmetric center, this knowledge of phases, whether it is a symmetric phase, enantiotopic phase, diastereotopic phase, what kind of this phase is, will become very important, very important. So basically all these things you must be knowing, depending upon what is the demand of chemical reaction and what are the information you are required to predict the outcome of these reactions, you must be aware of all these factors. So consider, if this is let's say I have just talked about a general molecular structure, since this reaction involving a charged species, nucleophile which is charged species, these reactions will be generally governed by charge controlled reaction. Means this is looking for positive charge. So where there could be a positive charge, this is also important question, isn't it? So where are there possible charges? If you consider properly, this is a little positive charge, this is a positive charge, this is a positive charge, and this is also positive charge, this is also positive charge, right? So this negative charge will interact with this point, or this negative charge will interact with this point. How will you decide? How will you decide? This can exactly interact with this part, this can interact with this part, because both centers are positive. And you know, if you have a elementary knowledge of organic chemistry, if this nucleophile will interact with this proton, positively charged hydrogen proton, this reaction will, the outcome will be completely different. This would mean simply proton abstraction, which will give an intermediate called enolate, resonance stabilized enolate, isn't it? And if this nucleophile interact with this center, the resultant reaction will be called nucleophilic addition at carbonyl center. It will result into tetrahedral intermediate. Outcomes are different. If let's say two paths, I am either telling, just to simplify, if this is the portion, if this is the situation, and this is, let's say, denoted by X, so that it could be considered nucleophile as well as base. If this negatively charged species interact with this part of the system, and it comes down like this because it is a positively charged, what is the result? Result will be proton abstraction, H abstraction. Result would be like this. This would be resonance stabilized. This is called enolate. Isn't it? It now has become what? Electrophile. This electrophile. The nucleophilicity of this X negative species has make this substrate itself as an electrophile. Isn't it? And let's say if this path 1, this is the path, if this interacts this way, outcome will be different. It will turn into what? This negatively charged, and this Nu, and this is what? Tetrahedral intermediate. This is what? Nucleophilic addition. Isn't it? This is proton abstraction. And if you examine it much more seriously, this reaction is somewhere, if you try to address the mechanistic part of this reaction, this is the part I am considering, that whether this will react this way or this will react this way. This is something related to outcome here. And if it's something, we often talk about mechanism. What would be the mechanism? And if you have a little understanding of organic chemistry, you may consider this part of the reaction as SN2 reaction at hydrogen center. Although this kind of terminology you will find very rarely in the text, because that is not usual way of representing things, but it is in some way SN2 kind of reaction at hydrogen center. And it is as what? Nucleophilic addition as sp2 carbon center. Nucleophilic addition in sp2 carbon center. And if you try to examine much more, little more deeper, what is the basic thing? This thing involved, if you try to relate it with the molecular orbital bonding, what is this kind of thing? This is basically, this requires CH sigma star bonding. Where this delivers pair of electron? Delivers toward CH sigma star antibonding. And where this attack happens? This requires CO pi star antibonding. This attack involves. Okay, alright. Now, whether this will react this way or this will react this way, how will do it? This requires further, you are clear to this part. What has it has required? It has required some geometrical, molecular, structural, electronic polarities kind of properties that are required, isn't it? And if you want to decide that whether this will react this way or this way, you need further information. You need further information. What kind of information? Thermodynamic information. Thermodynamic information. You need kinetic information. Let's say if I talked about thermodynamic kind of part, and you better know any reaction would proceed mechanistically if the reaction system is able enough to provide activation energy required by the electrician. Every organic reactions or every chemical reactions has a characteristic threshold energy of activation. Let's say if this is the X minus species, this is the potential energy axis, this is the X minus species, this energy level is here, and the substrate energy level is here, let's say here. If I consider this is the energy level, which is required by the attack of the kind of CH sigma star bonding. If I say this is the energy level which is required by CO pi star bonding, means this has to attack, if this has to attack to this bond, anti-bonding, or if this has to attack to this anti-bonding, the activation energies involved is these two paths are different. Kind of, it will require EA activation energy and will require E2 activation energy. And you understand, E1 is much more greater than E2. Alright? And if you do bond enthalpy calculation, means which bond is breaking, because new bond form will be CX bond, in this case also CX bond, and breaking bond is a pi bond, the other involves a sigma bond. And if you do some bond enthalpy calculation, you may get possibility of equation considered by this equation, T del S. This is the equation. Suppose the reaction is at 25 degrees centigrade, normal reaction in given solvent, ether solvent fixed. Means solvent side and temperature side of the reaction is well controlled, the reaction is in the same pot, it has the same pressure, they have the same thermokinetic parameters have been fixed for both these reactions. Then how or which path this reaction will choose automatically will be decided by these factors. And suppose if at this level, it is clear that in both cases the reaction is at least feasible. Delta G and bond calculation tells you. Yes, means for E1 and E2 both are feasible paths for the reaction in given condition. So thermodynamic consideration says that reaction is at least feasible in these two terms. Then who will decide what will be the outcome, whether this will be formed or this will be formed? Then it will require kinetic information. Means if this is the path, then what is the order of kinetics? This is the path, what is the order of kinetics, and which is kinetically more favorable? Then you have to apply one type equation of this. If you have a k value for this equation, then apply Arrhenius constant and Arrhenius equation and want of kind of equation, and there is a common equation you will derive in this sense, and those kinetic equation will give you some kind of, it's like kind of K1, K2 you will find in is this term delta GR terms, is this kind of reaction, these kind of equations will give you that kinetics of which side will be more preferable. Alright. Then you will be able to decide that which path is going to be feasible, which side it will react. If the one side the k values is much lower and corresponding time, let's say if I choose this path, the k value in this calculation is much lower at this delta G, that means this reaction will require much high, it will take a years of time with that rate constant. That means this path is less feasible. But if I found calculating this side by using the delta G corresponding to this and found the rate k constant much higher than in this case, and this reaction is feasible or possible in some real time, it may take 1 or 2 hours, then you will simply say, because since this reaction is a very slow kind of reaction, this kinetics of this kind of reaction is very slow and this kinetics order is very fast, so this reaction will happen much faster in much simpler way than to wait for this path to happen in a year. Alright. Then you will be able to predict the outcome of this reaction. Alright, what I told is stereochemical factors, geometric factors, molecular orbital factors, molecular structural factors and thermodynamic factors, all when you apply to the same point, then you are able to predict something. Then probably you can say this is going to be possible most important path, not that one. Then you are able to comment on something called kinetics. Alright. Suppose if somebody comes and some fellow says that if I increase the concentration of X minus, what would happen? If you are aware that this reaction is a first order reaction, you may say, oh, there will be no effect. Or this is a reaction is a zero order reaction, there will be no effect. But since you know this is the SN2 type of reaction, and this is the SN2 reactions are generally second order reaction, so concentration of this negative species also do matter for the rate of reaction. You will simply say, no, of course if you add the base, the reaction will be much faster in this direction. And the kinetic factors favors both path equally, then who will be deciding? Thermodynamic factors, isn't it? So when you know these kind of things, you attain a level power of prediction in organic chemistry. And when you have some level of power of prediction, you begin to enjoy the subject. And your approach will automatically change. Alright? So whether be this way, let's say, then there are other things. If I have a little or small variation in this structure, carbonyl functions, the reaction behavior will be different. Suppose we have R kind of X. This is the reaction system, and I have a nucleophile. When X is equal to simply CS3. Means if you have a nucleophile, what it would be the reaction? R and X, and this is what I'm going to say anyway. Let's see. This is the reaction. This is the tetrahedral intermediate. After the addition of this nucleophile to this substrate, and you know this tetrahedral center at carbon center which is having a charge in a solution system will be highly unstable. Very highly unstable. If you quench it, very soon as it get forms with some protic acids, you will result with this kind of, this will result in this kind of product, which is the typical reaction at carbonyl center in the case of Grignard reaction, you know. Grignard reagents react this way. What happens when you have, let's say if you have this kind of acetone and you react with RMGX, what is the typical path of reaction? R comes to this fellow, R, and these two groups are like this. This is the tetrahedral center, and you then work up with acid. In laboratory terms, we said we are going to work up in acidifying the solution. This will get protonated and you will result with this product. There will be a product. This is the product. But if consider this is the case, if you consider a little different case, in a different case, when you consider R kind of carbonyl and this is X, and you add any nucleophile to this center, where X is unlike the earlier case is not CS3, but X is something like this Cl, Br, I kind of halides, or OCl kind of OCS3 group, OCO CS3 kind of group, means I am talking about the esters, per esters, acid halide derivatives. Okay, if this kind of reaction this kind of group is present in the form of X here, the reaction product will be completely different from the earlier one. What it will happen? When you will add a nucleophile, this will change like this. This will go like this. Sorry, this will go like X and this will go like this. This is the tetrahedral center got formed. In earliest case, what you did? When you will act like this, it will attack here, electron will move to this. This is the flow of electron, the movement of the arrows that you know in the organic chemistry. But in this case, this is also a tetrahedral medium. What I did say in the first case, it was a CS3 group in the first case, and since CS3 group has a no leaving tendency, it has no leaving plan, it cannot leave. So what happened? You just followed the reaction by quenching it up with the proton, you resulted into alcohol at Grignard way of reactions. And if this group is a leaving group, better leaving group, what will happen? This electron pair will return and this minus X will leave and will result in what? Substitution reaction at carbonyl center. This will result into what? Called substitution reaction. This is called nucleophilic substitution, and the first one called nucleophilic addition. And which entity which make this difference? That substitution will happen or addition will happen? This X. If this X is having some leaving tendency, this will move out, leave this center, and this tetrahedral intermediate will decompose and will decompose to regain its original structure and will form sp2 carbon carbonyl system, and the reaction system will see a substitution at carbonyl center. And if this is not the case, this will get trapped and you need to quench it, and tetrahedral carbon will remain intact and will result into some alcohol kind of product. Alright, so who is making this difference? And now, how fast this reaction would be, whether this will leave or any other competitive group is present that this will leave, this kind of things will be addressed by something called leaving behavior, a leaving tendency of this substituent. And leaving tendency itself of this substitution requires the knowledge of its molecular structure, requires the knowledge of its acidity, its pK values, means something related to electronic and solution behavior, thermochemical behavior, kinetic behavior, kinetic levelity of this group, thermal stability of this group. These kind of information you are aware in the case of X, you would be able to predict the rate of reaction, preference whether this will move or this will move. Alright? And now, let us say if I just, this is the part of reaction that which kind of reaction is going to happen, is going to happen here. But let us say, if you are going to add this was the carbonyl center, I am trying to bring, is it over? Alright, I am trying to bring in stereochemical factors, that how stereochemical factor influence the outcome. Let us say, by this case, we have considered this symmetric carbonyl center, where these CS3 were the same. Let's say I am changing this part. Now this C2 axis got dissolved. There is no more C2 axis. The molecule is not symmetric there is no axis of symmetry. Still there is a plane symmetry. There exists sigma B and sigma H kind of plane. No sigma B, there exists a sigma H kind of plane, planar symmetry. If you pass a plane through the molecular plane, it will be a symmetric structure, but there is no more C2 axis. If you rotate it by 180 degree, the resultant structure will be different. Means this phase now has become what? Diastereotopic phase. Now the stereochemical outcome of this reaction will have a difference. Of course it is CS3. If you add this CS3MgX kind of Grignard reagent, if you add this reagent to this center and to this center, since this is symmetric, C2 axis is there, this is symmetric, alright, it is called isotopic phase. The reaction outcome, whether this molecule, this magnesium, this CS3, whether it comes from back side and attacks the center, or it comes from above the plane and attack this center, the outcome in this reaction are going to be same. Means the path, the trajectory. I am not considering that whether will this act at this center or will act at this center. Now I am considering in both the cases this is going to act at this point, act at this carbonyl carbon center, alright, at this kind of center. But like other first one cases where we are just choosing between these two different path in a structural sense, that this part of structure of this carbonyl will be participating in a reaction, or this part of the reaction center will be participating in this reaction. But now I am keeping the reaction center constant, but just considering the way it will approach the substrate. Even this may leads to a different significance, different molecule, different kind of stereochemical outcome. In this case, if it is a chiral center, the outcome of this reaction, like this kind of alcohol that you will result in, CS3, this kind of alcohol, this will be plus minus, this will be racemic mixture, this will be RS kind of thing. And the percent of plus or minus or R or S means at T60, at T20 or 60, 40, this kind of thing. This enantiomeric complexion will be governed by something called the nature of this chiral center. This chiral center and the substituent associated with this chiral center will decide the outcome of this reaction, that whether it is going to be R or S, be dextrorotatory kind of optical behavior of this product or levorotatory kind of product of this behavior, what would be the degree of rotation. Everything has to be controlled by this chiral center. This chiral center would be guiding this CS3 entity, nuclear species out of this whole Grignard reagent, that which way you have to come, which side you will approach. Got my point? Means if it is like this, which side this will attack on this phase, on the above side, from the above side or from the below side, this will be controlled by this center. And both the cases the product will be same, different. And to understand that what is going to be the product in both the cases, there is some generalization, there is some empirical rule that famous organic chemist Crames have described a rule, Crames rule that we call. Crames rule will help you understand by seeing the structural information and nucleoside what could be the outcome of this reaction. Crames will help you in that sense. Crames rule will help you. So this is what I am trying to emphasize, how the geometrical and stereochemical information may help you to predict the stereochemical outcome in organic reactions. Alright, this is the part of the things are clear. And you must be able to understand that this thing that we are considering, one thing is constant. One thing is constant. What is constant? Constant is thing, I am considering the interaction of charge or with charge. Whatever example that I consider, either the first two case or the last one case of different stereo optical came, doesn't matter what have been the cases, I am considering this constant kind of thing, that here is a nuclear charge and here is a positive charge, or here is the positive charge, here is the positive charge. Depending upon the magnitude of positive charges or the corresponding difference in the activation energies or thermokinetic parameter, I am able enough to predict that whether this will react with this or react with this, or some other general principle kind of, people will talk a hard and soft interactions, and people will even tell you that kind of difference in polarity, there is a high stronger charges, there is a weaker charge, there is a stronger charge. This is taken by high strong dipole moment, the mu associated with this point, mu1 point kind of, and this hydrogen kind of, here mu, direction of mu and magnitude of mu of CH bond kind of thing and CO bond kind of thing. This if I consider this first and this consider this second dipole moment associated with CH bond and CO bond, some fellow will come and tell you, since that mu d in the first case is much higher than this case, mu d in the second case, that's why this will preferably attack to this point, because this is why this will happen, because this whole reaction is basically a charge controlled reaction. Electrostatically, this part of electrostatically or charge controlled reactions. This is the part. Means in all four cases that we have discussed here, everywhere we are talking about that this negative charge will interact with this positive charge, or this negative charge will interact with this positive charge. Depending upon the magnitudes, some people will argue that since the magnitude of charge will decide ultimate attraction, ultimate Coulombic attraction in both two cases, so Coulombic law will tell you that which path would be preferred. And if the force is obviously much higher due to the higher charge in Q product of the charges, since the magnitude of the product of these two charges, like these two charges are here, Q1 and Q2, is much higher than in the case of magnitude of Q1 and Q3, then this path will be followed, because in terms of potential energy, the energy drop in this case, the potential energy in this case will be much lower, which will reflect in the terms of threshold energy of activation. That's why that path will be kinetically and thermodynamically favored, and this reaction will happen much faster than the point that I have discussed just a little while before, kind of things. But if somebody comes to ask you that this is the just one kind of reaction, this is an electrostatically controlled or charge controlled reaction, there is a other kind of reaction like Diels-Alder reaction, there are no charge involved, pericyclic reaction, single step entropically rebelled pericyclic reaction, there is no charge involved, all that is involved is a symmetry of orbitals. Those reactions are considered orbital coefficient dominated reactions, where you need a good understanding of molecular orbitals and symmetry of orbitals, and that will help you to do the organic chemistry. So having all this kind of knowledge, stereochemical, thermodynamic and kinetic kind of parameters will help you to predict something in organic chemistry. And once you are able enough to predict something in organic chemistry, then you should console yourself that you are on a right path. Alright? So this is enough for this day. We will take next lecture if you demand for. Okay, alright, thank you.